My name is Ronnie Green, and I have the privilege of serving as the Vice Chancellor for the Institute of Ag and Natural Resources here at the University of Nebraska-Lincoln. Welcome to Hardin Hall and to East Campus for this last installation for the academic year in our inaugural year of the Human Lectures. The Human Lectures have been enabled for us by a gift by Keith and Norma Human, longtime supporters of the university and supporters of agriculture in the state of Nebraska and beyond, so that we can have dialogues amongst the university community and stakeholders of the university in areas related to food, fuel, water, landscapes, and people. And I'm pleased that in all of the lectures this year, this is the 6th one in the series, Keith and Norma have been able to be with us for the lectures, with the exception of one where there was a death in the family. They're here today. Please join me in welcoming and thanking Keith and Norma Human. Our lecture is being web streamed today live for folks to be able to join us remotely across the state and the region. It also can be accessed on campus cable channel 4 and Lincoln channel 21. And some of you will recognize that our previous lectures have been replayed through the NET network in that fashion. They also are archived at humanlectures.unl.edu. If you go to the web, you'll be able to find all of our previous lectures there. We've been really pleased with this inaugural year. We've been able to welcome people like Professor Swaminathan, the first winner of the World Food Prize, to our campus, our own Stephen Banziger, our own Roberto Linton, the new founding director of the Dougherty Water for Food Institute, former Senator and Governor Bob Kerrey, as well as Mr. Stuart Brand to our campus. So it's been a really phenomenal year in this first year of our lecture series. Today, we finish off on what I think is a really high note by welcoming back a Nebraska native to our campus to give us a lecture in the bioenergy arena. And before I start, I'd just like to introduce to you, his father is here today, with him, Max Keasling, down on the front row from Harvard, Nebraska. Out west of here, Max, thanks for being here and being part of the lecture. It's a pleasure to introduce Dr. Jay Keasling to you and to tell you a bit about his background. As I mentioned, he is a Nebraska native, grew up on a farm near Harvard, Nebraska, that's in Clay County, about 90 miles west of here. He received his bachelor's degree from UNL, graduating with high distinction, and then received his master's and PhD degrees at the University of Michigan, now one of our Big Ten colleagues, by the way, Jay. He is currently the Hubbard Howe Jr. Distinguished Professor of Biochemical Engineering in the Department of Chemical and Biomolecular Engineering and the Department of Bioengineering at the University of California at Berkeley. He's the Chief Executive Officer of the Joint BioEnergy Institute in Emeryville, California, which is one of 3 bioenergy research centers funded by the U.S. Department of Energy to advance developing the next generation of biofuels. He also is a Nanyang professor at Nanyang Technological University in Singapore and is Associate Laboratory Director of the Lawrence Berkeley National Laboratory and Director of the Synthetic Biology Engineering Research Center. He's the recipient of the inaugural Biotech Humanitarian Award from the Biotechnology Industry Organization, or what we know as BIO, awarded in 2009 for his efforts in fighting malaria through work to produce a microbial-based version of the most powerful anti-malarial drug at a price affordable to the poor. He also received the 2010 Presidential Green Chemistry Challenge Award from the United States EPA and is the recipient of numerous other awards as well. In addition, he's an accomplished scholar and co-author of over 230 refereed journal articles and a partner on 14 patents. We're very pleased to have Jay on our campus today. Please join me in welcoming him for his lecture, The Bold Future of Alternative Energy. Dr. Keasling.
Thanks very much. It's a pleasure to be home and to see all of you friends. So as Ronnie said, I'm going to talk to you today about the bold future of alternative energy. And I first want to just mention a couple of conflicts of interest. I'm from a corn farm in Nebraska where we raised corn and pigs and cattle and soybeans. And because of those pigs, I'm not on the farm. I'm also the founder of a couple of biotech companies that are working on alternative fuels and alternative chemicals from cellulosic feedstocks and from things like corn. And I run a BioEnergy Institute. So with those conflicts of interest in mind, I want to talk to you about the challenge that we're facing as a nation and as a planet. The U.S. alone uses about 100 quadrillion BTUs of energy, and it's really hard to get a perspective on how much energy that is. But the main point here is that 83% of that energy comes from fossil fuels, things that have been locked well underground for millennia, carbon that's been locked underground and that is now being released into the atmosphere. Now, if you just take as a baseline the amount of carbon that's being put into the atmosphere, that's that green line going there, and the temperature changes over the past 100 years or so, you can see a pretty strong correlation. And in fact, right now, the carbon dioxide in the atmosphere is at the highest level that it's ever been recorded, even going down in the ice cores back, say, many thousands of years. So there's clearly an issue with the amount of carbon dioxide that we're putting into the atmosphere and its potential impact on the planet in terms of the temperature rise. Now, as all of you might know, we get the majority of our gasoline, our diesel fuel, our jet fuel, all of our transportation fuels from petroleum. The petroleum is pumped up, a thick, gooey liquid that's refined in refineries. We get these liquids that we use as transportation fuels. We also get nearly many chemicals that we use on a day-to-day basis. So if you just look around you at the plastic on the table that you're sitting at, the finish on the floor, on the wood, the screen here, the ceiling, the paint, all of that has in some form come from petroleum. So it's a huge resource for our fuels and for our chemicals. Now, if you just look at a typical barrel of oil, we get about 20 gallons of gasoline from every barrel of oil. We get about 4 gallons of jet fuel and about 10 gallons of diesel fuel. So that's roughly 80% of the barrel of oil. The other 20% of that barrel of oil goes into all of the other products, like the finish on the floors, like the plastic on the tables, as well as many of the other chemicals that we use on a day-to-day basis. Now, if we just look historically at the growth in transportation fuels over, say, the last 70 years, the growth has been pretty dramatic. You can see that it's gone up over 8-fold in terms of gasoline. Diesel fuel, shown in red, is growing pretty dramatically, and jet fuels, which really came into use in the early 70s, are growing at a steady rate as well. So our use of this petroleum is growing rather dramatically. Now, if we take the Department of Energy projections out several decades, out to 2035, you can see that gasoline is leveling off with the hope that we will be replacing some of that with E85. But diesel will continue to grow because there's a growing market in diesel cars. They've become cleaner. They're now on the roads in California and many other states. So we will see diesel grow as a fuel, and gasoline probably level off. Now, that growth in energy use, in use of petroleum, is coming at the same time that our discoveries of oil are peaking and declining. So on this plot, I show basically the discoveries of oil over the last few decades. And at the very bottom is the United States. And you can see that in the United States, discoveries for oil peaked in the early 70s. And then they've been tapering off ever since. Now, where does that gasoline, diesel come from, that growing demand? Well, it comes from other countries. And so you can see that these other countries are beginning to peak. Now, we don't really know when oil production will peak for a couple of reasons. One, as the price of gasoline, of oil as itself goes up, there's more encouragement for engineers to discover oil underground and geophysicists. The other issue is that many of the countries that have the vast energy reserves, this is a well-kept secret because it's part of their national, core to their national economy. So we really don't know when peak oil is going to happen, but it's probably right around this time. And discoveries then will decline over time. Now, if we just look at oil use in the U.S., you can see that this is the domestic production of oil right here at the bottom, and the total consumption of oil is at the top. And how we're making up for that difference in the consumption and the U.S. production of oil is through importing oil. And this became really dramatic in 2005, where oil imports were 60% of consumption. So we were importing an enormous amount of oil. And then President Bush and his energy team became quite alarmed with this, and they started the wheels turning for the development of some of the institutes, like the Joint BioEnergy Institute that I run in Emeryville, California. Due to the economic crisis, though, the consumption of oil dropped pretty dramatically over the last few years, and now we're importing roughly half of the oil we use on an annual basis. It's expected that that will decline, but that assumes that consumption in the U.S. will level off as we get more efficient vehicles and as we develop advanced biofuels that are American-made. Now, the result of that is that this has added a great deal to our trade imbalance. So I'm showing here just a plot of the balance of trade over the last 3 decades. And you can see that in the early 80s, trade was almost balanced, and then it became very imbalanced over time. And this is about the period where we started importing a large amount of our oil. And you can see down here in 2005, where the trade imbalance was at its worst, that's where we were importing the greatest fraction of our oil consumed. The imbalance in our oil consumption accounts for roughly half of the imbalance in trade. So if we could eliminate that imbalance in oil consumption, we would eliminate half the imbalance in our trade deficit. Now, the challenge, though, is that the U.S. on the world stage is a small country in terms of population. We have a little over 300 million people. There are 6 billion people, 7 billion people on the planet, and it's growing. And half of that population is in India and China. And those countries are growing, their economies are growing at a double-digit pace, or have been in the past. And those people, I can tell you, are very much want the same lifestyle that we have here in the U.S. So as a result, the U.S. Department of Energy anticipates that the world energy demand will grow pretty substantially over the next few decades, and not from the developed world, shown here in green, but from the developing world, places like China and India that want to have our lifestyles. Now, the result of that is that energy consumption throughout the world is going to rise dramatically. And I just show here what's anticipated for U.S. energy consumption. You can see that it's growing, but at a fairly slow pace. But now look here in red. This is the growth of China's energy consumption. And we know it's growing at this pace because from 2000 to 2010, it grew dramatically. So that's history. And India is just starting to increase its energy consumption pretty dramatically. So all of this is going to add up to even more shortages of oil as our discoveries are peaking. Now, what that's going to do in the near term and beyond is impact the price pretty dramatically. Now, of course, we can't predict exactly what the price of oil is going to be, but if you just take this kind of worst case scenario, the Department of Energy is suggesting that it could get to $200 a barrel, right? So that would double the price of gasoline in the U.S. And that would be a dramatic change for our economy. There are some predictions, though, that it could level off at around $120 a barrel, but I don't think anyone seriously believes that it's going to level off at that low a number. Now, I talked about the amount of carbon dioxide put into the atmosphere and mentioned how it has been rising the last few decades. Well, now, just imagine what's going to happen when China and India and the other developing countries in the world start using that much energy. So this is what we project will be the carbon dioxide emissions from these developing countries, and it's going to grow dramatically. So the amount of carbon dioxide we're putting in our atmosphere is nothing like what it'll be in a few decades if we don't change our ways. And the problem with that amount of carbon dioxide in the atmosphere is the predictions are that it will take centuries. Even if we stop using fossil fuels right now, it'll take centuries for that to correct. And so the increase in temperature will continue on for many centuries. Now, there are ways around this, and there's hope for the future. And one of the hopes for the future is ethanol as a renewable fuel. And I think you know quite a bit about this in Nebraska because there's a lot of it going on in Nebraska. You all know about raising corn. That corn is then sent into a bio-refinery where yeast ferments the starch and the glucose released from that starch into ethanol. And the corn takes up carbon dioxide from the atmosphere, and when you burn the ethanol, you put it back into the atmosphere. Now, if we just look at worldwide ethanol production, it's grown really dramatically this past decade. So in the green is the ethanol for fuel, in yellow the ethanol for beverages, and in red for the industry. So the good thing is that we're not increasing our consumption of ethanol by humans, but we are increasing our consumption of ethanol through burning it as a fuel, as a replacement for gasoline. Now, if you look at the top ethanol producers in the world, the U.S. is number 2, but not far behind Brazil. Brazil produces almost all of its ethanol from sugarcane. It's got a very efficient system for producing ethanol from sugarcane. China's starting to produce more and more ethanol from corn and wheat. And then you have smaller players like the European Union and India starting to produce it. But you can see that the U.S. produces a substantial amount of that ethanol. Now, as I said, the corn takes up carbon dioxide from the atmosphere to make the corn plant, and when you burn the ethanol, you return the carbon dioxide to the atmosphere. So we have the possibility of having carbon neutral fuels, that is, not adding any more carbon dioxide to the atmosphere. Now, there are a few challenges with corn as a crop for producing ethanol, and I realize that this might be heresy saying these things about corn, but it does require quite a bit of water, requires a lot of fertilizer. But one of the biggest issues is that corn is used to feed cattle, and cattle, of course, are for food. And so there's this challenge of how do we balance food and fuel if we use corn as a feed crop. One of the prime challenges with corn is the amount of energy that it takes to raise corn right now. So this is just a breakdown of all of the energy that goes into producing corn. And what you'll see here is that roughly half of the energy in producing corn goes to produce nitrogen-based fertilizers. So ammonia takes a huge amount of energy to produce. We use natural gas for that, and that puts a lot of carbon dioxide into the atmosphere. If we could engineer corn to fix its own nitrogen, then we could reduce by half or more the amount of energy needed to produce corn. Unfortunately, that's an enormous biological problem, something people have been working on, but something that needs a large attention because this is a huge potential area of research. And the challenge, and this is a rather busy plot, but the challenge with corn for producing ethanol is that you get just barely positive energy out of it. So shown here are all the areas that we use energy for in producing corn-based ethanol. We use it for the corn production. We use it to transport the corn into the bio-refinery, to turn that corn into ethanol, to distill the ethanol from the fermentation broth. So that total energy is just a little bit short of the energy that you get out of the ethanol. And that means that you get just barely more energy out of the ethanol than you put into making it. And that's a problem right now, and a problem that we need to fix. If you consider all of the other things that we make from corn, like corn oil and corn starch and corn flakes, then we actually get a net positive energy out of it, about 34% more energy than it takes to produce it. But there are great examples out there. So, for instance, sugarcane in Brazil, you get about 8 times the amount of energy out of it than you put into it. That's a huge increase over corn-based ethanol in the U.S., and I think it's something that we should definitely strive for in the U.S. Now, I want to talk to you about other crops that we could use to turn into ethanol and into other fuels, and one of those is switchgrass. And if you just do a simple energy balance on switchgrass, you'll see that you get about 4 times the energy out that you put into it. Now, what that switchgrass would replace is the corn that we're now using to turn into ethanol. And I just want to mention this crop right here. This crop is Miscanthus giganticus, and I think you can see where the giganticus comes from. This guy isn't a 4-year-old. He's actually a grown man, fairly tall. This grass is a native of China, and it grows to be about 12 feet tall. They've been growing it on plots at the University of Illinois over the last 2 decades, and it produces a huge amount of biomass with very little fertilizer. It has a very interesting property that as it grows, it takes up nitrogen and nutrients from the soil. It also appears to fix some of the nitrogen. It puts them into the plant as it grows, and then in the fall, when it dies back, it sends all of those nutrients back into the soil. And so they cut it about snowfall, or after the first snowfall, and pretty much all of the nutrients have gone back into the roots for the next crop. And so you're cutting basically carbon off of the field. It's a really interesting potential bioenergy crop. Now, the U.S. Department of Agriculture and the U.S. Department of Energy recognized many years ago that we're going to need other alternatives to corn if we want to be able to produce a lot of our energy, and these have to be non-food crops. So they did an assessment of all the possibilities in producing biomass to turn into fuels. And these are shown here. The main take-home point here is that we're going to rely on dedicated energy crops, shown here by the green bar, over the next few decades in order to grow the amount of biomass. Now, this is baseline assumptions. If you assume that agriculture is going to be extremely productive, we can get somewhere on the order of 1.5 billion tons of biomass. Now, what does that 1.5 billion tons of biomass really mean to you and me? Well, let's just compare it to the amount of oil we used in 2010. So in 2010, we used 7 billion barrels of oil. And as I told you earlier, roughly half of that was imported and half of that was domestically produced. So if we take that 1.3 billion tons of biomass and we burn it, you get about the same amount of energy as you do from the domestically produced oil. That's pretty substantial. And if you turn that into a biofuel with the conversion efficiencies that we think we can get to, you can get the equivalent of about 2.3 billion barrels of oil. So that's a little more than half the imported oil. That would be an enormous change in world economics and world politics. Imagine if we were sending the equivalent of 2.3 billion barrels of oil, that money, to Nebraska and states like that, rather than to Saudi Arabia and the Mideast. It would be a huge change in our balance of trade, and it would be a huge change in world politics. So this is what we need to strive for. Now, in 2007, Congress became very concerned about the imbalance in oil production in the U.S. and oil consumption, and also our balance of trade. And so they passed the Energy Independence Act. And in that act, they specified that by 2022, right out here, we should be producing about 35 billion gallons of renewable fuels. And that could come in any form that we wanted and could produce at the time. A lot of that would come from corn-based ethanol. But starting in about 2015 and beyond, they expected that that would come from biomass, things like switchgrass and other crops, dedicated bioenergy crops that we would be turning into those biofuels. Now, if you just take that 35 billion gallons, and I apologize, this is now in hectares and in liters. I got this from a Brit. And so I'll just translate it for you. If you just take 35 billion gallons, that's 133 billion liters, and you say, how much land is it going to take to produce all of that fuel? And we look at just corn grain itself. It would take roughly 35 million hectares to produce 133 billion liters of ethanol. That's roughly 25%, 1/4 of the farmed land in the U.S. to get to those levels of fuel. That would be a huge displacement in corn. If you take switchgrass, which is a little less productive than corn grain and corn stover together, you'd need about 28 billion hectares of land. And if you use this Miscanthus giganticus, this very giant grass, you'd need roughly 10% of our cropland. But in any case here, the take-home message is that a large amount of our cropland would have to be changed from corn to another type of crop that we could use to produce these fuels. Now, I talked about this growing concern with carbon dioxide in the atmosphere. What would these fuels do for the amount of carbon dioxide put into the atmosphere? Well, this is actually a study that comes here from the University of Nebraska, where they've done, Ken Vogel and his group have done some great studies on switchgrass that's been planted in several different farms throughout Nebraska, South Dakota, North Dakota. And they did an assessment of how much carbon dioxide you'd save by producing ethanol from switchgrass rather than using petroleum to produce gasoline. And it's really pretty dramatic. And I actually met with Ken today, and he actually told me that they've got studies coming out it's even better than this. It even gets better. But the take-home message here is that you reduce almost completely the amount of carbon dioxide that you would otherwise put in the atmosphere by burning gasoline in your car if you burn ethanol made from switchgrass. There's two important issues here. One is that you're reducing the amount of carbon dioxide you're putting in the atmosphere because the plant takes up that carbon dioxide. The other issue is that these grasses are planted, they're perennials, and so they grow over and can be cut for many seasons. And they actually have microbes surrounding them that fix carbon in the soil. So these plants actually fix more of the carbon, take it out of the atmosphere, and put it into the soil. And so we're locking more carbon into the soil than what we would with corn or another crop. So this, the switchgrass looks to be a great crop for the future. Now, I want to talk a little bit about the science I do on a day-to-day basis, because it's an important aspect in turning something like this biomass into a biofuel that we can actually use in our automobiles. So biomass is really complicated. This is a picture, a micrograph of a plant cell wall, and this is from a dead plant. So the plant cells would live in here, and they would secrete this plant cell wall. And this is what's left over after the plant dies. You basically have these cell walls left over. So this is straw, this is trees that have died, and they have these rigid cell walls. And these cell walls are really complicated. They consist of basically three components. Lignin, which is not a sugar, and then two components that are sugars, called hemicellulose and cellulose. And cellulose, shown here in blue, is in these bundles, these fibrils. These are good sugars. They're roughly equivalent to the sugars you get out of starch. Hemicellulose contains different kinds of sugars that are not quite as good, that yeast don't metabolize so well, but they can still be used as an energy source. So basically three components. Now, there's a lot of data here, but the take-home message here is that roughly 70% of any plant is sugar. You take a tree, a pine tree, you take a eucalyptus tree, you take rice straw, you take switchgrass, you take corn stover, roughly 70% of any plant is sugar. And those sugars we can turn into fuels. The question is, how do you get access to those sugars? Well, the way you get access is you tear the plant apart. So in the biorefinery, once you haul in the straw or the hay, you need to first remove the lignin. There's an old saying about lignin that you can make anything from lignin but money. And it's pretty much true. There's nothing really we can do with it. It's a highly connected polymer that's in the cell wall. It gives the plant its rigidity. We can't engineer a plant to eliminate the lignin, but it's there to protect the plant as well. It keeps all the critters away from those sugars that they might want access to. And then once we have cellulose and hemicellulose, we use a cocktail of enzymes to break it down into sugars. Now, just to give you some idea about the strength of these sugars and these polymers from these plants, if you think about starch, you mix starch in water and it'll eventually dissolve. And we need only one enzyme to really break starch down into sugar called an amylase. If you think about cellulose, though, it's really strong. This shirt is cotton. Cotton is pretty much 100% cellulose. And yet, you and I know that if you put this shirt in your shirts into the laundry, they don't dissolve. But yet it's pure sugar. Well, the reason it doesn't dissolve is because that sugar is bound up into very strong fibers. And those fibers don't come apart. And the only way to break those apart is to add enzymes. So the reason that your shirts and my shirts don't have fuzzballs on them is because the detergent companies add in enzymes that clip all those little fuzzballs off the cotton. The cotton eventually frays. Well, those same enzymes, or very similar ones, can be used in the biorefinery to break down those sugar polymers into the individual sugars that then the microbes can use. And then the final step is for a microbe, and right now we use yeast, to consume those sugars and turn them into ethanol. And this is a process that humans have been mastering over centuries. And so we know a lot about this from brewing beer and wine. But there are some challenges in all of this. We'd like, in the ideal world, to have a plant that would have a lot of these good sugars in cellulose, as few sugars in hemicellulose as possible, and as little lignin as possible. But there are some constraints on the plant. We'd like to have a process that removes the lignin. The processes that are currently used for removing the lignin tend to leave a lot behind, and that makes it difficult for the enzymes to release the sugars from that biomass. Some of that biomass contains inhibitors that end up poisoning the enzymes and the microbes that produce the fuel, so we'd like a biomass that doesn't have those inhibitors that get released. We'd like cheaper enzymes to break down that cellulose into the sugars. Right now, the enzymes alone cost about $1. Add $1 for every gallon of ethanol that's produced from cellulosic biomass, so it's an enormous cost in cellulosic biofuels. And finally, we'd like to have microbes that would not just produce ethanol, but would produce fuels that can be used in jet engines and in truck engines as diesel and jet fuel replacements. Right now, we use ethanol as an oxygenate in gasoline. And unless you have a flex fuel car, you can't use more than 10% ethanol in that car, or you'll invalidate your warranty on that car. We'd like to push that to 15%, but the car manufacturers are fighting that because there's a challenge with the engines and having too much ethanol in it. You can't use ethanol at all in jet engines. It doesn't have the full punch energy as a gallon of jet fuel, and it can't be used at all in diesel engines. So we need fuels for these other modes of transportation. So the institute that I run in Emeryville, California, works on this entire pipeline from sunlight all the way to fuels. And I want to describe just a few of the things we're doing that we think are going to end up in next generation energy plants and into biorefineries. So I want to address a few of these challenges. One of the challenges is this problem of getting the lignin away from the cellulose and hemicellulose in the plant. And this really reduces the amount of sugar and therefore increases the cost of the fuels. Now, there are two ways you could get around this. One is that you could develop better pretreatment methods that would completely remove the lignin and give you lignin-free cellulose and hemicellulose. Another is that you could engineer the plant to have a reduced amount of lignin or a different lignin. So I want to first talk about engineering plants. It's actually a very exciting area of research. So this is a better chemically derived structure for lignin. It's a really complex chemical that's in the plant cell wall, and it's very highly interconnected. It makes it challenging to break it apart. So one of the things that researchers at JBay are doing are engineering stops in these lignin polymers. So this is a way to make shorter lignin. The plant still has the same amount of lignin, but it's shorter, it's not as interconnected, and that makes it easier to extract it from the plant. And we do this by engineering the chemistry inside the plant, get it to incorporate different monomers into that lignin, and the result is that we get plants that grow just as well as the wild type plant. So here's the plant we started with, here's the plant with 4 different plants with engineered lignins in them, and they release a significantly greater fraction of their sugar when they're pre-treated. So this is exactly the result we want. Now, on occasion, though, this engineering doesn't work out quite so well. And that's shown here. So here's a wild type plant, and here's a plant with a different type of engineered lignin. And you can see it's much shorter. It's easier to tear apart, but there's no real plant to have any biomass from. So this isn't the ideal situation. And you can see it grows much more poorly. But one of our researchers, Dominique Loki at JBay, found a way to take this mutant plant and express different genes in it that would allow it to grow and yet produce more cellulose and hemicellulose, the sugars, and less lignin. And just to show you how dramatic that is, here's a micrograph of the plant cell wall. These are basically holes in the wall where the cells were and where nutrients run up them. And he's now taken those plants and filled them up with sugars. So these plants are just stuffed full of sugars. And there's a substantial increase in the amount of sugar that we can get from that engineered plant. And that's shown here with these. You can see that the amount of sugar released has gone up pretty substantially in these engineered plants from the wild type plant. So big impact in the amount of sugar you can get out of the plant by changing the lignin in the cell wall. Another thing that you could do, an alternative, is that you could come up with a better pretreatment process, a way to better extract the lignin from the plant cell wall. And to do this, we want to change the pretreatment methods. Now, these pretreatment methods often involve high temperatures, high pressures, and extremes of pH. So low pH, a lot of acid, or very high pH. Now, researchers at JBay have been experimenting with a completely new process for extracting lignin from biomass, and it involves something called ionic liquids. These are really liquid table salt. So if you can imagine table salt being a liquid rather than a solid, you mix it with the switchgrass, it completely dissolves the biomass, and when you add water back to it, you get cellulose that's really pure that comes out of the process. And this just shows a picture of how those plant cell walls change. So here's the starting plant cell walls. You mix them with ionic liquids, they begin to swell, they start to release all the sugars from their biomass, and you add water back and you get these fibrils going through here, and this is pure cellulose, pure sugar coming out of those plant cell walls. Now, just to test if these are actually better biomasses that we're getting out of the process, you add enzymes back and you look at how quickly it releases sugars. And there's, again, a lot of data here, but this is the pretreatment method that's been most widely accepted. It takes about 70 hours to release the sugars from the biomass. With the same biomass, using this different pretreatment method, these liquid salts, we can actually remove that same amount of sugar in about 7 hours. So that's a significant cut in the amount of time it takes to process the biomass and a significant reduction in the cost. And this process works for eucalyptus trees, it works for pine trees, it works for switchgrass, it works for corn stover. So it works pretty much regardless of any type of biomass you want to mix those ionic liquids with. Now I want to talk just briefly about these inhibitors that start in the biomass and end up poisoning the microbes that produce the fuel. And these inhibitors come from the biomass itself. They're actually chemical decorations on the biomass. They get released in the pretreatment process and they poison the microbes. Now, the challenge in doing research with plants is that there's been very little funding for plant research in the US. And it's really been only lately through some of these efforts with the advanced biofuels that there's been a lot more funding, especially through the Department of Energy, for working with plants. And so the strategy in JBay was to find the genes that are responsible for putting these chemical decorations on the plant cell walls and eliminate those genes completely. So Henrik Scheller, a researcher at JBay, went in with several gene candidates, knocked out those genes. We get a significant reduction in those inhibitors in the plant cell wall. And a surprising result to us is that we got a substantial increase in the sugar released from those genetically engineered plants. And what we think is happening is that those inhibitors are actually linkages between the lignin and the cellulose and the hemicellulose, and that by eliminating those, we're actually breaking those linkages and allowing the sugars to be released more readily from the plant cell walls. Now, you never know in science when you're going to have a beneficial result, when you're going to have a result that doesn't work at all. And this is one of those results that we weren't anticipating at all, but that actually turned out to be pretty great, positive for us. So if you take a plant and you challenge it with a plant pathogen, in this case it's a fungus that infects plants, you get these large lesions on the plants. And whenever you engineer a crop, you have to test it against these pathogens because the plants might face these pathogens out in the field. So we actually challenged these engineered plants, the ones with the fewer inhibitors in their plant cell walls with these pathogens, and you can see that they had much less impact on the plant. So this is actually a really positive result that the plant is able to survive that pathogen even though it's been mutated to release its sugars in a much easier way. Now, in the last part of my talk, I really want to talk about this last aspect of the problem, and that is, how do we engineer a microbe to produce all of the fuels that we might want for our transportation infrastructure? One of the real challenges for the airline industry right now is that the European Union is going to start requiring that any plane that lands in the European Union have a certain fraction of its fuel as renewable. That means a bio-based fuel. And there aren't many bio-based fuels around, so airlines are scrambling to come up with alternative fuels that they can put in those airplane engines. And in fact, there have been many tests now in the US where they're actually running them on partially renewable fuels. And those percentages that are required to be in the planes when they land in the European Union will increase over time. So this is a real challenge for both biology and for the airline industry. Now, our approach to this is to take the microbes that naturally produce ethanol, yeast and E. coli that we have been using over the last 4 decades in modern biotechnology, and change the chemistry inside the cell to produce hydrocarbons that are identical to the hydrocarbons we now get from petroleum. So how do you do that? Well, the first thing you have to consider is what kind of fuel you want to produce. So you've got to consider the engine type. Are you going to put it into a diesel engine, or into a gasoline engine, or into a jet engine? It's got to have a high energy content. One of the challenges with ethanol right now is that if you have a flex fuel car and you put E85 in your car, you'll get about 70% of the distance that you would on a gallon of gasoline. When I was talking to folks at Exxon, they were very against selling E85 because they said, you know, people have this idea they'll buy a flex fuel car, they're used to every weekend going in and filling up the tank of their car, and suddenly they put in E85 and they discover they can't get to the next Saturday, they have to fill it up on Thursday, and that's the last gallon of E85 they put in their car. So you got to think about energy content. It's got to have the same energy content as our current fuels. It's got to have good combustion quality. People don't want engines that knock when they're driving down the road. You can't have cloudy things because cloudy things plug up fuel filters. It's got to be volatile. It's got to be stable because we're going to store it. We're going to ship it through pipelines. Another challenge with ethanol is that we can't ship it through our pipelines. We have to ship it by rail car or by truck. It can't be smelly. People don't like smelly things, even if they're in their cars. It can't be toxic because I can guarantee you that it's going to get into the groundwater. Every fuel station leaks. Gasoline leaks out of cars, so it's going to get in the ground. Can't be miscible with water. That's one of our challenges with ethanol, is that it picks up water, and so you have to redistill it. And it can't be $4,000 a gallon. So these are some of the fuels that we're working on producing at JBay. We looked at all of the chemistry going on naturally inside microbes and inside plants, and we looked at all the kinds of molecules you might want to have, diesel fuels, jet fuels, and gasolines, and we came up with this list of chemicals. And I'm just going to briefly go through these because these are actually important components of fuels. Now, these components, where these got these long chains here, these are the components that we find most often in diesel and jet fuel. They're long chain alkanes, and they've got a lot of power when they're in a compression engine. So we need these kinds of fuels. Now, this is glycolysis. This goes on inside the cell for the scientists in the room. Glucose comes into the cell and gets turned into these intermediates, and cells use this to produce fatty acids that make up their membranes. One of my graduate students, Eric Steen, working with LS9, discovered that we could produce a fatty acid ethyl ester by changing the chemistry inside the cell and actually produce a diesel that would be directly suited for diesel engines. And this is a centrifuge tube where it's got E. coli growing in it, and this is the fuel floating at the top here. If you take this out and you put it under the microscope, these are the little E. coli that are floating in this medium, and here's the blebs of diesel fuel that they've made and secreted out of the cells. Now, what's important about this, and that's so different about how ethanol is made, so when you make ethanol, it's completely mixable with the water that the cells grow in, with the fermentation broth. And that means that you have to distill it to get it out, and you have to add a lot of heat and a lot of energy, and therefore a lot of money to distill the ethanol out of the fermentation broth. But in this case, it's an oil. It's diesel fuel. And you all have probably made vinaigrette. You add a little vinegar and balsamic vinegar and olive oil. You mix them together, but eventually when they sit out, they phase separate. The oil goes to the top, the water, vinegar goes to the bottom. Well, that's the same thing that happens with this fuel. You add in the sugars, you add in the microbes, they produce the fuel, they secrete it outside the cell. You turn off the impellers and it floats to the top, and then you skim it off. It isn't quite that easy. The companies like Amyris and LS9 that are now making this use basically a big cream separator to separate the cream, in this case the fuel, from the milk, the fermentation broth, where the yeast are. Now, this works really well because we've engineered the chemistry inside the cell to make the exact hydrocarbon that you want to use in a diesel engine. You can do the same thing and tailor-make jet fuels or gasolines. Now, if you're in a place like Brazil that has a completely integrated bioenergy infrastructure, they centrifuge out the cells and they spray dry them, and those become cattle feed because they're high protein. They take the fermentation broth, which is rich in nitrogen and phosphorus. They cart it back out to the fields and spread it on those fields as fertilizer for the sugar cane, and then the fuel they take off and they sell. Now, these hydrocarbons, these straight chains, are really good in diesel fuel and in jet fuel. But if you're in Nebraska in the winter and you have all of those straight chain hydrocarbons, you'll end up with a wax in your tank. It'll gel up and get hard. And if you're at 35,000 feet in the atmosphere, I can guarantee you don't want that to happen where it's really cold. So the way you battle that is you add some branches in. And those branches break up the structure so that rather than having a wax, you actually have something like number 2 diesel that will flow even under very cold temperatures. And so we needed to be able to install those branches in these molecules to make diesels and jet fuels that would be usable under cold temperatures. Now, this comes back to a project that we worked on several years before and that Ronnie actually mentioned in the introduction. When I started this work on advanced fuels, I was just coming off of a project that was funded by the Bill and Melinda Gates Foundation to engineer a microbe to produce an antimalarial drug. This antimalarial drug is artemisinin. It's actually going to be coming out this year from our microbial process. We engineered a yeast to take in sugars, transform them into this antimalarial drug, and produce it in very high quality at a very low price. Now, as it turns out, this drug is a hydrocarbon. It's about the same molecular weight as diesel fuel, has many of the same properties of the molecules that we'd like to put in diesel fuel and jet fuel. And on top of that, we had a microbe that had been engineered for high-level production of this antimalarial drug. So we took that microbe and we've engineered it now to produce a gasoline replacement. We've engineered it to produce a jet fuel replacement, and we've engineered it to produce a diesel replacement. And one of these molecules, this diesel replacement, has very similar properties to number 2 diesel. In fact, almost identical to number 2 diesel, except in a few cases where it's a little better. So cetane number is the equivalent of octane number that we have for gasoline, but this is for diesel. It's got an almost equivalent cetane number, very low freeze point and a very low cloud point, which means it can be used either at high altitudes or under very cold temperatures, and it has a high density, which means that you will have about the same energy as what we get out of number 2 diesel. So a great replacement. Now, just very quickly here in the end, some of these fuels that we make, like this jet fuel replacement, are toxic to microbes that want to produce it. So this is an unfamiliar curve for you, but this is a series of curves, and basically where you see no change, that's where the microbes didn't grow at all, because this fuel is very toxic to the microbes that produce it, and that's no way to get a high-level production of a biofuel. Well, it turns out that when you take antibiotics, and if they don't work, the microbes that those antibiotics are fighting probably are resistant to the antibiotic due to pumps. These pumps, and this is a structure of one of those pumps shown here, exist in the microbe and they pump drugs out of the microbe. Well, it turns out about 3 decades ago, someone found out that when you spray Pine Sol on your kitchen counter, and if you spray it a lot, that the microbes that it's fighting will become resistant to the Pine Sol. And they'll actually eat the Pine Sol and grow on it. That's one story about using a lot of these antibacterial soaps and things that we have to worry about, is that the microbes eventually become resistant to those. Well, we decided that we could actually steal those pumps and use them to engineer the microbes to become resistant to the fuels that they're producing. You actually install those pumps into the microbe, they pump the fuel out as the fuel is being made, and they keep it out so that the microbe can grow in the presence of it. And again, this just shows the microbe growing in the presence of those fuels with these pumps in them, and they work very effectively to allow the microbe to both produce the fuel and pump it out. Now, just in closing, I want to address this last issue of engineering microbes to use the biomass directly. I described to you the fact that for every gallon of ethanol we make from cellulosic biomass, these enzymes we add about $1 to that gallon of fuel. Now, the best case scenario would be to have a microbe, a yeast, that makes your fuel and secretes these enzymes so that you can do this all in one process. So Greg Bokinski, a postdoc in my laboratory, decided that he would take our fuel-producing microbes and engineer them with the ability to use things like switchgrass and eucalyptus directly. We treat the biomass with these ionic liquids to extract the cellulose and hemicellulose. The microbes secrete the enzymes to break down those complex polymers and at the same time produce the fuels that we can now use. And we've shown that we can produce a gasoline replacement, a jet fuel replacement, and a diesel replacement directly from switchgrass or eucalyptus. And just as a quick experiment, as a fun experiment, Greg went to his backyard and actually collected biomass. He collected twigs and branches and various things from his garden, treated it with ionic liquids, and actually turned it into fuels. So what I've talked about today, in large part, is how we replace petroleum as a feedstock. I feel very passionately about this area, having come from Nebraska, from a farm where we can actually use the farm to produce a lot of our fuels. But if we're producing hydrocarbons that are identical to the gasoline, diesel, and jet fuel that we now produce from petroleum, there's no reason why we can't produce all of the other chemicals that we now get from petroleum, but from sugar. And this is, I've actually pared this number of chemicals down. It's a huge number of chemicals that we get from petroleum, things like pantyhose and shampoo and clotheslines and luggage, etc. We should be able to produce all of these from sugar. And imagine what that will do for the rural economy in places like Nebraska. I think we have a bright future. We're going to need a lot of research in this area, but I think it could be great for the Nebraska economy. These are the people at the Joint BioEnergy Institute, and they are the ones who did all the hard work here. I'm only the reporter on what they've done. I'd like to thank them for their work. I'd like to thank the U.S. Department of Energy for funding this work. I'd like to thank Ronnie for inviting me here to give this talk, and to all of you for being here and listening to the talk. And I thank you very much. Sure. And then I've got your last slide in there too.
So if we could get the lights up, we have some time now to have questions from the floor for Dr. Keasling. And I think there are some roving mics. Jill has one down here, and we have one up top as well. So if you have a question you'd like to ask Dr. Keasling, please raise your hand. Here's one in the back.
What should be the role of government in supporting research and the use of the fuels therefrom?
Could you ask the question again?
What should be the role of governments
Yeah.
to support not only the basic research, but more importantly, the transition then to the marketplace of the fuels themselves. And I'm talking about price supports, direct and indirect, and use benchmarks and use contracts.
It's a great question. I think the first thing we need from government is a steady hand. We need steady policies over many decades. If you look at how long it took petroleum-based fuels to grow to the place they have right now, it's many decades. And we have to anticipate that it's going to take many decades in order for biofuels to become established. And so we need steady government policies first, no matter what those are. But I think second, we have to have some rules from the government about preserving food. We don't want fuel to ever replace, or fuel crops to replace food crops necessarily. We've also don't want the government necessarily to pick particular crops. They shouldn't be picking winners and losers. They should let the marketplace do that and be willing to support any crop that it is, just as they've supported, say, corn over the years. And frankly, I think that corn, I've said a few things that maybe negatively about corn. I think corn could be a crop for the future, but it's going to take a lot more research to develop it that way. But I think a steady hand and not picking winners or losers. I think the other thing the government can do is it can have long-term contracts for fuels. So one thing we've been discussing with the Department of Defense is having long-term contracts for fuels for planes and tank engines, for instance. They could, for instance, let long-term contracts that would allow biofuels companies to take those contracts to the bank, get loans for building these facilities, and they'd have, the steadiness of those prices over a long period of time.
Jay, I noticed you didn't mention anything about isobutanol. What's your experience or feelings about its potential?
I think there are a lot of great alternatives to petroleum-based fuels, and isobutanol is one of those. It's not one that we necessarily work on at the Joint BioEnergy Institute, but it is one that's definitely out there. GEVO and DuPont are both working on isobutanol, so I think it's got a lot of potential. It can be used to substitute for gasoline. It can also be dimerized and turned into things like jet fuel and diesel. So I think it's got a lot of potential. It's just one of those out there. And the great thing about it being in the energy industry, it's the largest industry on the planet. And just to give you some idea of the size of the energy industry, think about ExxonMobil. So it's now number 2 in market cap to Apple, but huge market cap, one of the biggest oil companies, and yet it has, 5% of the petroleum market. It has a very small percentage of the petroleum market, and that means that all of these companies can play in this. There's room for everyone and many different types of fuels. So again, I don't want to pick winners and losers. The marketplace should do that, and it should be on economics.
I think behind the camera, sir.
Jay, you did not either mention the work we read about in the newspapers where they're producing diesel fuel from algae.
Yes. So, I think that, so we're not funded to work on diesel from algae, but again, I think it's a great source of hydrocarbons. There's a company in the Bay Area called Solazyme. They work on algae that produce oils. They actually feed the algae sugar, so it's pretty much the same as the fermentation processes I described. But again, I think it's an interesting alternative. There are some challenges with growing algae because they have to be grown in systems. You have to get light and carbon dioxide in. But again, I think there's plenty of room for them to play in this area.
Well, just about every week I cart yard waste to my curb. And I was fascinated when you said that it can be turned into fuels. Do you see any potential for turning everyone's yard waste into fuels so we're not actually planting and harvesting, but just taking what's found in our yards?
Sure. I think that can be a small fraction. In another version of this talk, I show a pie chart that shows things like yard waste, municipal waste, and that. And it's potentially up to 5% of the amount. It could produce up to 5% of the amount of fuel. So it would be a small fraction of that 1.3 billion tons of biomass, but nonetheless significant. And I think we're going to have to look everywhere for waste. And paper, as you know, is pretty much all cellulose. So it's a great source for sugars for feeding microbes.
I wonder if you might just talk a little bit about why the approach going for energy from microbes and from algae as well. Is this to leverage the existing system of our energy coming from liquid fuel sources, and why not further look for energy coming from, say, solar or wind sources?
Right. If you think about transportation fuels as an energy carrier, they're really special. If you look at the amount of energy in a gallon of gasoline or a gallon of diesel fuel, it's amazing. They are one of our, on a volume basis or on a weight basis, they are one of the most substantial carriers of energy. In fact, our batteries now that we're electrifying cars with are about 1/100th of the energy carrying capacity per pound of transportation fuels. And in fact, getting batteries to be at that energy carrying capacity of transportation fuels is a real goal of a lot of the energy programs in the Department of Energy. And what we're seeing now is that there are passenger automobiles coming on the market that are either have a small battery in them and are hybrids in some way, or plug-in hybrids, or we're seeing all electrics even come on the market. But their range is pretty limited. It's limited to about 40 miles, say, or some have even said up to 70 miles. But still, a very narrow range, and these tend to be smaller cars. It's going to be a long time before we have batteries that we could use in something like a truck. In fact, if you think about a truck that hauls goods, it would take almost the size of the truck itself in all battery in order to propel that truck. There'd be no room for the goods that it hauls. And I don't think we're ever going to see battery-operated airplanes. So we need something to replace liquid transportation fuels. And the truth is, we have $3 trillion worth of infrastructure built around liquid fuels. It'd be a shame to have to replace all of that if we could just replace the biology to produce those fuels from a different source.
I think we have one up top.
Oh yeah, there it is. Jay, sorry about that. You had mentioned that this could be a boom for Nebraska. One of the things that would be an advantage for rural Nebraska, if the scale of this was small enough that you could have them, the plants that are producing it spread out around the country rather than a large ethanol plant in 3 or 4 communities. Have you thought about, or do you have any idea about what an economic scale would be?
Yeah, there are a number of estimates out there, but I think generally it's going to be, a bio-refinery that's collecting biomass from about a 30-mile radius, something like that. Of course, it depends on the intensity. I was talking to Confocal today, and he said, well, there are all these corners on these center pivot irrigation systems would be great for energy crops. You could plant corn in the middle and something like switchgrass on the corners. And of course, that means that if you don't have full fields dedicated to producing your energy crop, you're going to have to go out farther in radius. And the challenge there is that you have to truck the biomass to where you want to go, but yet the biorefinery has to be a significant enough scale that you can actually get the economies of scale of having it in place. So I think around that range of about a 30-mile radius is what we're going to see.
We'll take just a couple more questions. So Al on the back.
Okay, Jay, as you see as your crystal ball, do you think you're going to be working more with biomass that's coming from a waste of, say, the corn product we raise for corn, like the stover, so forth, or do you see specialty crops being planted like switchgrass as you move forward with this?
I think it's going to be a combination of those. So if you looked at that, it was probably hard to see, but that chart that showed the predictions for biomass out to 2030, roughly 2/3 of that was coming from waste. So corn stover, municipal wastes, and the like. And about 1/3 of that was coming from dedicated energy crops. I think that if you could raise corn, for instance, and you could have maybe if the corn were self-fertilizing, you could get the kernel of corn and use that for the cattle feed, and you could collect the stalks at the same time and use those, which would otherwise be waste, and use those for producing fuels. So we could have our cake and eat it too.
Last question up top, I think.
So it's very exciting to hear about all the research going on in J-Bay. And one quick question is, as some suggestions for young scientists and future researchers, what's your idea about what kind of research we should do so we can help with this transition and make our future brighter?
It's such a great area to be in right now because there's funding for it. And I think there's a real interest in it. I mean, there's room for plant scientists. There's so much work to be done in the plant area. This is, long-term research efforts. We need the government to be supportive of that over the long term, but I think that's a huge area of research. Looking at microbes in the environment and how they degrade plants, and trying to tap into that natural biology and use it for our benefit. And then some of the work I talked about at the end, where we're engineering microbes to produce completely new things. There are so many chemicals out there that we could end up producing from sugar that we don't right now. I think it's just, there's a lot of chemistry to be done as well. So it's a bright future in the area.
Would you please join me in thanking Dr. Keasling for his lecture? As a small token of our appreciation for the lecture, Jay, and as a way for you to remember it, we have commissioned a medal that each of our lecturers are receiving for the human lecture. So please accept this as our token for you to remember this day at Nebraska, and thank you so much for being here to give the lecture.